What's up, ladies and gents? Welcome back to another e-learning experience with your host, Mr. Cloud. And we're going to be transitioning to a new phenomena in earth science momentarily. Last week, we talked about physical and chemical weathering. And naturally, you're going to talk about weathering first, and then you get into the movement of rock or the movement of sediment, which is called erosion. Here I am looking down upon the earth, and we can focus in to the Gulf of Mexico. And if you notice, guys, when you take a look at all these different states here, a lot of them are separated by rivers. Okay, and rivers will be the conversation that we're having today. It is the most dominant form of erosion on Earth's terrestrial surface, and really, it's the main topic of conversation that we're about to have. All right, let's get into it right now. Okay, so first things first, let's take a look at one of Earth's 7 natural wonders, the Grand Canyon in Arizona. I'm sure you know what cut this canyon, or maybe you don't, but it is a river. It's actually the Colorado River, and it just gouged out this canyon over the span of millions of years into this amazing place. If you ever get the opportunity to get to the Grand Canyon, get there. All right, it's one of those religious experiences for any geologist out there. Okay. Now, I was always intrigued by rivers and streams, and growing up, I did some hiking. Oh, there I am. Nope, this is not me over here. That's my friend Matt. This is Mr. Cloud right over here. And maybe we can focus in a little bit. And there I am. And there I am. And maybe one more time. Mr. Cloud at age 15, folks. And no, that's not a hunchback. That's a poncho right there. It was raining that day. We were hiking up to the top of Mount Washington. Okay. But why do I bring this up to you guys? Okay. Because right behind me over there, all right, is a river, and it's transporting sediment downstream at pretty high velocity. And you can tell it's high velocity just because of the white water that you see here. So it probably has a pretty steep gradient, and it's kind of ripping through the landscape. It's a very young stream right there. Okay. So what is a river? What is a stream? Well, pretty much when the ground is saturated, or if it's impermeable, when the rain falls, right, it's going to start to accumulate. Some will infiltrate into the ground and some will run off. That's the first step, guys, of creating a river. Then you can get what are called rills and gullies, which are these really tiny channels that kind of spread out in all directions. And then they may form channels. If they form channels, they'll become streams, and then streams can become larger river systems. Okay, let's get into some more of that terminology right now. Okay, all right, let's do that. Okay, boom, let's do it. So streams, guys, are running water erosion confined to a channel. And when you have one stream making its way into a larger stream, or one river making its way into a larger river, we call those tributaries. There are smaller streams that flow into larger streams. All right, the picture you see down here is the west branch of the Delaware River, and that's in the Catskills in upstate New York. All right, guys. And growing up, I used to have a ski cabin right on the west branch of the Delaware River, as a matter of fact. So this week is going to be similar to last week. I'm going to have questions that are embedded here in the PowerPoint presentation in the screencast. And the first question is coming at you right now. Question 1. Using page 3 of your reference tables, identify 4 rivers in New York State. So you're going to have to go to page 3. You're going to have to look it up and try to figure out what those rivers are. And which of these rivers could be classified as a tributary. Okay? Google Doc style coming at you for this week's first half of the week homework. All right. Now, other terms. Watersheds. A watershed is an area that's drained by a river system. That's all it is. A watershed could be as small as a watershed in the back of your house in the Catskills, or these small little brooks making its way into a larger stream. That could be a watershed. Or a watershed could be the size of the eastern part of the United States, like where we have the Delaware watershed, or the Mississippi watershed, or the Columbia watershed in the Pacific Northwest, or the Colorado watershed. So it can really, really vary dramatically. Okay, divides separate watersheds. So usually it's a change in elevation. Okay, so if I do this right here, okay, if rain falls, if the rain starts falling down, the rain can either go towards the left or towards the right, and my fingers will be the divide. Okay, it's that change in elevation causing the rivers to go in different directions. One great example is the Continental Divide, which is going right through the Rocky Mountains. That's going to separate the Mississippi watershed from, let's say, the Colorado watershed. Okay, what else we got going on for you here, guys? Let's talk about, I think, um, factors that affect stream velocity, which will be another major topic in the class. Okay, so what I'm going to do here is I'm going to break down the first factor that affects stream velocity. After that, it's going to be your job to look up the other two. So let's get into the first one right off the bat. Okay, so let's do this. Let me try to do a little bit of writing here, right on the screen for you. Okay, all right, guys. So I'm going to go freehand. I'm going to separate this screen into two separate halves. On this side, the left side over here, we're going to go and we're going to make a stream over here, which I'll make in blue, and then another stream over here. I'm going to call this stream A, and here's stream B, okay? And then I guess I'll use kind of blue to kind of show you the stream making its way downhill and another stream making its way down this way. So there are three factors affecting stream velocity, and I'm hoping the first one should be pretty obvious to you, okay? What's the main difference between stream A and stream B? Well, you could have guessed it. It should be, hopefully in your mind from topographic maps, the one A over here has a steeper gradient. It's just steeper than the one at B. It's higher up in the mountains potentially, it has higher elevation. So if I were to roll a ball, all right, down a steeper slope, what's going to happen? Well, the ball's going to go faster down the steeper slope and it's going to go slower down the more gentle slope. It's as simple as that. All right, so our first factor here, ladies and gents, okay, is going to be, okay, gradient. That's what it's going to be. Okay, and that's the slope of a stream. The relationship is, guys, as the slope of the land increases, stream velocity increases as well, and vice versa. Okay, so what's going to be your job? Here's your job now. Okay, question number 2. There are 3 factors that affect stream velocity. Gradient would be the first factor. A, identify the next 2 factors that affect stream velocity. And B, explain the key relationships that exist. Move myself up a little bit so you can see it. Include an image or drawing to help you explain. So what I would do is I would identify the factor, provide the relationship, present a drawing or an image that shows it. Then move on to the next one. All right, guys? So far we've had 2 questions thus far, and both questions have 2 different parts. So about 4 separate mini questions going on here. Okay? Now, how do streams transport sediment? Let's move on to the next section here. Okay? Now, when you take a look at this, guys, all right, there are 3 ways in which a stream is going to carry sediment. The first, guys, you can see down here, these are most likely conglomerates. They could be all different types of rocks, but most likely they're sedimentary rocks, right? And they're hopping along the bottom. We call this, guys, the bed load. Okay? All right, that's the bed load down here. All right? Now, if you have smaller particles, they can actually be floating, or they can be what we call in suspension. We call that the suspended load. Okay, and that's most likely maybe some sands or some silts like that, or maybe some clay that's in there too. And then lastly, guys, there's the dissolved load. Okay, so I like to compare this whole situation to a bowl of chicken soup. Okay, so you have your bowl of chicken soup, and there are carrots in there, and there's pasta in there, and maybe some spices or some salt like that, right? Now on the bottom of the bowl of soup, there's going to be maybe some, I don't know, maybe your pasta falls to the bottom, maybe a large piece of carrot falls to the bottom. The bottom is the bed. That's the bed load. Then you have pieces floating around, maybe some onions floating around in there, something like that. That's a suspended load. And then the salt that's in solution, we call that the dissolved load of the stream. And these are the 3 ways that a river can carry sediment. Okay? All right. So what's another question you can be asked about rivers? All right, let's do that. All right, well, what you got to do is take out your reference tables, guys, and you're going to turn to a familiar page. All right, I believe it's going to be page 6. But first, let's ask a question and then give you an example of how to use that page. Okay, so the general rule, guys, is when stream velocity increases, sediment load, which is the amount of sediment that it's carrying, the turbidity increases, and then also the size of sediment also increases. Okay, so what we're going to do is we're going to go to page 6 right now. After we see ourselves a question, I'm going to jump right into it. Okay, so here's question number 3 for you. And the question number 3 has a couple different parts to it. Here's the first question. We're going to do it together right now. How fast would a river have to be traveling to transport a particle with a diameter of 1 centimeter? How would you do that? All right, so let me escape out of this. And we're going to go to our reference tables. And I'm going to move myself over this way. And let's take a look at how this actually works. All right, so let me pick up my tool for you here. I'm going to use arrows to help you. Hopefully it'll work out better this way. Okay. And if you guys remember what it was, I believe it was 1 centimeter in diameter. So then I'm going to use, all right, my arrows here to help me out. I'm going to use a red arrow, why not? So you find 1 centimeter. Oh, the 1 centimeter is right over there. Then you make your way across like so. When you hit the line, you stop. I feel like you've done this a bunch of times throughout earth science. And then when you can, I'm sure, guess it, when you hit the line, you stop, and then you make your way down from that line. Okay? Now, I tried to do this the best I could freehand. I wouldn't recommend doing it freehand. I would recommend using a straight edge or something like that to be more, I guess, more precise than I am. So what's the answer, guys? Well, it would be totally acceptable, ladies and gents. All right, guys, if your final answer was 50 centimeters per second. Let's give you another example now. Okay, so I'll change my color here for you. I don't know, what do you guys want to do? Let's do purple. Okay, we're also going to do an arrow. You could be asked something different, like the opposite. What if a river was flowing, let's say, at 1 centimeter per second, which is pretty slow? All right, what could it actually transport? Okay, what type of sediment and what size of sediment? Okay, so we're going to go with 1 centimeter per second. So here's the one down over here. All right, there's my 1. I'm going to make my way up to the line, and I'm going to stop. And then I'm going to make my way over that way and figure it out. Now, don't get confused. This axis is a little bit silly over here, but this is 0.01 centimeters. So this should be, I believe, 0.02, 3, 4, 5, 6, 7, 8, 9.1. So each one's going up by 0.01. So your answer should be 0.02 centimeters in diameter. Okay. Now, if I look on the other side over here too, what this does is it gives me all my different types of sediment, clay, and you saw this with sedimentary rocks, silt, sand, and pebbles like that. Okay. So a river that's going 1 centimeter per second, I make my way this way, and it can carry then sand, it can carry silt, it can also carry clay. Okay, that's how that works. It can carry pebbles, it's just not going fast enough, cobbles or boulders either. Okay, so there's an example of how to actually use that chart. All right, now if we go back, guys, to what we were just doing, we're going to erase that there, get rid of that. Shoot over this way. We're going to present again. We're going to move over this way, and we're going to read through the rest of the questions together. Okay. So B says, a river is traveling at 100 centimeters per second. List the types of sediment it can carry. Types would be sand, silt, clay, pebbles, etc. C, a stream is traveling at a rate of 500 centimeters per second. A drought happens. A drought is when you don't have rainfall for a long period of time. And the river slows to a rate of 1 centimeter per second. Identify what size particles will be deposited by the stream. And D, what is the maximum size sediment a stream can carry if it's traveling at 200 centimeters per second? All right, guys, so let's get those done this week. All right, and there you have, in the PowerPoint itself, another diagram for you. All right, now, rivers will cut valleys in the shape like a V. Okay, a V-shaped valley, right? Whereas glaciers will cut valleys that are much wider and much more gradual. We call those U-shaped valleys. So repeat it to me, V-shaped. V-shaped valleys for rivers. Okay, now we talked about how velocity shifts and changes with gradient changing and 2 other factors that you're going to figure out. But what I want to do with you now is talking about how water in a river will actually change velocity at different locations in a river. So what I'm going to do is I'm going to pause the video right now. I want you to take a break and then come back to it.